A one-dimensional array gives us the ability to work with sets of data in one variable. After we see that, I'll also show you the next way we will use pointers as a way to look into an array. Suppose we wanted to keep track of people's ages and calculate the average age. If we have to keep each person's age in its own variable, our code would look like this. The real downside to this is that it's really hard to add more people. Not only do we have to add a variable for each new person, we also have to change the formula for average age as well. An array is a single variable that can contain many values at the same time. For our age example, we'd want an array to hold the ages. If we only had 3 people, this is how we'd declare the array. Just add how many spaces you want in the square brackets. That will cause the compiler to allocate 3 positions for that one variable. Once you've declared the array, the positions of the array behave like variables. The positions are numbered starting at 0, and we specify one of the positions by putting its number in the square brackets. We call this indexing the array. In this example, I declared ages so that it holds 6 ints. They will be numbered from 0 to 5. I can store anything into the array with an assignment statement. We read this ages sub 3 gets the value 13, and it has the effect of putting the 13 in this position of the array. One of the real powers of arrays comes from the fact that we can use a variable to specify the position we're interested in. For example, if I make an integer named I, and I give it the value 3, I can use ages sub I to access that position of the array. It is very common that we want to do something to every position of an array. For example, we might want to print them all out or initialize them all. To do those things, I typically use a for loop to make an index variable that takes on the positions of the array. In this example, I've declared an array named array to have 3 positions and put some values into it. This for loop starts I at 0, so the first time through the loop, it adds the value in array sub 0 to sum, which started at 0, so the sum will be 42. Then I gets bigger by 1. It's still less than 3, so the loop will add a array sub 1 to that running sum. Adding 60 to 42 makes the sum be 102. I gets bigger by 1. It's still less than 3, so we add array sub 2 to sum. 102 plus 21 is 123. I gets bigger by 1. It is no longer less than 3, and the loop stops. We use this loop structure so commonly that it has its own name. This is a walking through an array loop. Notice that I've used that walking through an array loop to sum up the values in the array. Dividing by the size of the array, with a typecast to make it do real division, gives me the average. Remember how we had to change the formula for average when we didn't have arrays? With arrays, if I have one more person's age, I just make the array bigger by 1. This code for calculating the average doesn't change. In C, we also have to be careful because the compiler will not initialize the array's values. It could contain whatever was laying around in memory when the array got allocated. So we often have a walking through an array loop that initializes all of the positions of the array. One other important difference between C and other high-level languages is that in C, an array does not know how big it is. We have to keep track of the size ourselves. In this example, I used a pound define, but we could have used a variable if the array wasn't always the same size. In C, we can pass an entire array into a function. In this example, I declared array to be an integer array, and I've used an initializer to give it its values. I've passed that whole array as the first argument to ArraySum. Notice that I also have to pass in the size of the array so that ArraySum can walk through the array, adding the values to a running sum as it sees them. That looks like an input parameter, a pass by value parameter, because we didn't make any effort to pass a pointer. However, let's look and see what's really happening. So I have the code here in CLion. I've put 2 breakpoints. The first one will let us look at the array before we make the function call, and the second one will let us see what the array looks like inside this function. So if I run this in the debugger, here we are in main. My array looks just like we'd want it to look. And if I go to memory view and dump the stack, I can look here is our array because I can see the 3, 5, 12, and so on. If I go back to here and continue, now I'm sitting at this breakpoint in ArraySum. And if you look at X, which we think is our integer array, its type is actually an integer pointer. And if I expand that, it just shows me the first thing. It has no idea that that was allocated as an array. So even though we feel like we passed the array into ArraySum, the compiler actually just passed a pointer to the array into it. And in fact, if we look at memory view and update for the new RSP, you can see here in our stack frame, we don't have a copy of the array. We have a pointer to FE40, which is down here. That's our array. So even though it feels like we passed the whole array into ArraySum, and it looks like it's an input parameter because we don't see any pointers, the compiler actually changes it to be a pointer to an integer, and it is an input-output parameter. If I change the values in that array inside ArraySum, the array that main is looking at will also be changed. It's important to note that even though the compiler has passed an integer pointer into the function, we can still use it like it's an array. So we can still index it the way we index arrays. Just like we can make pointers to individual variables, we can make pointers to specific positions in an array. For example, I've declared swap to have 2 input-output parameters, and its job is to swap their values. So the parameters are pointers to integers, and we dereference those pointers to play with their values. The net effect is exactly what we're hoping for. Their values get swapped. That function has no idea how the integers whose pointers are being passed into it are stored. They could be individual variables like this, and the result would be that Fred would be 20 and Merlin would be 42. We could also use this swap to swap values in 2 positions of an array by passing in pointers to individual positions of the array, like this. I've used the address of operator to pass in pointers to 2 positions in my array. Let's look at that in CLion. Okay, so here's our code in CLion. Let's just watch this run first to make sure it works. So it puts 42 and 22 into positions 3 and 4, says swap, and then prints out positions 3 and 4. We see the 22 before the 42, so it has swapped their values. Now I've put 2 breakpoints, one so that we can look at the array before we pass it in, and one so that we can see what is swap actually seeing. So if I run this in the debugger, here is our array, and there are the values. Now there's some garbage left laying around. Remember I warned you that it doesn't initialize arrays to 0? But I'm not looking at those positions right now, so I don't really care that there's garbage in there. I can see the 42 in position 3 and the 22 in position 4. If I go look at the memory view, I can find, if I look carefully enough, here is the 42 and the 22. So those are positions 3 and 4 of our array. Note that they're in position 4 is at position 5, 0. 3 is going to be at position 4C. If I continue, now we are in the swap, and you can see X is a pointer to position yada yada 4C, and it has a 42 in it. Y is a position to yada yada 5, 0. If we look at that in memory view, we can see here is the position to the 42, and here is the pointer to position 4, which has the 22 in it. And if we do step over, we'll watch those two. There, it copied the 42 up into temp. it put the 22 here. It put the 42 there. So it did swap those two values. Bottom line, arrays are used to hold a set of values of the same type. Once we've declared the array, we can use each position like it's a variable by indexing the array. That means putting a position number in square brackets after the array name. That lets us do anything you could do to a regular variable, even use the address of operator to get a pointer to a specific position. And that position number doesn't have to be a number. It can be an integer variable, and that lets us do things like walking through the array loops.